Nobody's saying that.
So the scalar product also has the names the dot product and the inner product of two vectors, and it's very similar to matrix multiplication. But you remember matrix multiplication, we had to take a row, we had to like bend it back into a column and then fire it forward to crash into things?
Yes.
In vectors, they're already column vectors. Vectors are never matrices bigger than that. They're always column vectors, and you just crash them in to each other. U1 times V1, U2 times V2, U3 times V3, and add them up. And it's called a scalar product because the result is just a scalar. It is not a vector. The answer you get is just a number. So vectors have a direction. A scalar is just a number. Yes. So if you have two vectors, vector v and vector w, and you want to do the dot product.
One second. For the grad tickets, JR, are you going to grad dinner?
I was planning on it.
I better put you on the table then.
Yeah.
Do it. Do you want to sit at my table?
I'm gonna order small tables. And invite the entire extended.
They're such hot. I'm just buying it to sell it online because their tickets are so good. I'm gonna make so much money.
And he sells the seats for hire.
That'd be long with somebody.
Can you go back to the one that I'm so sorry? Oh, was there something to write down?
Nothing to write down.
There was. There was.
There was, oh, just there's a little blank. Scalar product, okay.
Oh, that? Okay.
Yeah, it's the title.
There you go. Yeah, there's just a little box to fill in.
Little.
Well, I guess the middle box is pretty big. Always.
I guess.
Yeah, I can probably retire early. All good? So you take your two vectors as column vectors, you crash them into each other, the 2 hits the 1, the -3 hits the 2, you add up the pieces. And notation-wise, we write the dot product with a big dot in between. That's important because we're going to learn that vectors have 2 different forms of multiplication. They have the dot product and the cross product. It's the first time you've ever had 2 kinds of multiplication in one thing of mathematics. And if you had 3 dimensions, you could write them as column vectors, crash them into each other, pick up the pieces. Someone pushed in this thing. So all of your hole punches are going to be lower than normal. Roots. Ooh, how many people is this the first time they've ever used a hole punch? No. He secretly hole punches.
And
He practices because he's so.
It's like, if one of these days it's gonna happen in class, I don't wanna be unprepared. Properties of the scalar product. In this case, vectors act very much like numbers. If you do the scalar product in one direction, it's exactly the same as the scalar product in the other direction. Makes sense, because if you switch them around and crashed them into each other and added up the pieces, it would be exactly the same. If you have a number in front and then did the dot product, you could put that number in after you do the dot product, before you do the dot product with one of the vectors, or before you do the dot product with the other vector. That's just like multiplying three numbers together. You can put them multiplication any order you want. If you have the dot product with vector addition, you could do distribution with the dot product. And if you do the dot product with the zero vector, you have a dot product and the other vector's all zeros. You multiply them all together, pick up the pieces, makes sense that that would still be zero. So no, with the scalar product, there's no special property that you're like, ooh, I can't do that. Whereas with matrix multiplication, we had some special rules, right? A times B wasn't necessarily the same, well, almost never is the same as B times A. But now we get into some interesting properties of the scalar product. If you do the dot product, I like to call it the dot product, that's what I call it the most. So you hear me saying that the most. If you do the dot product, it is always the length or magnitude of the vector squared. Kind of makes sense, because if you had an A and a B element and you did your dot product, you would get A squared plus B squared, which is exactly equal to C squared. But the one in the box is the most important result. It just so happens that the dot product is equal to the length of u times the length of v times cos of the angle in between them. So if I had two vectors, vector u in this direction, vector v in this direction, and I put them tail to tail and had an angle theta in between them. If you do cos of that angle, multiply by the length of v, multiply by the length of u, you will get the dot product. This is, in a sense, a manipulation of your cosine law. So if you want to play around with this, right, if I had this triangle, you could use your cosine law to figure out things on that triangle. This is a super powerful result because it works not only in 2 dimensions, but it works in 3 dimensions as well. Get to use our word orthogonal again. If u and v are perpendicular or orthogonal, then the dot product is 0. It's a very quick way to find out if 2 vectors are perpendicular to each other. Because cos of 90 degrees is equal to 0, the other side of that formula would be 0. Since cos is positive in quadrant 1 and cos is negative in quadrant 2, if the angle between v and w, between the 2 vectors, is in quadrant 1, between 0 and 90, an acute angle, then the dot product is positive. If your dot product is negative, acute and ugly, yes. If your dot product is negative, then you know that the angle between your two vectors is between 90 and 180 degrees. And when the two vectors are parallel, the dot product will equal the length of V times the length of W. That one's not so easy to see. If we take that formula for the dot product and rearrange it, we can get cos theta by itself. And we can do some very powerful math. So historically what happens is people start playing around with this idea of vectors, they do some new math, they do this, like the dot product itself is really easy math to do. And then exploring it further, they're like, hey, there's a connection here between the cosine law, and we can then rewrite the cosine law with the dot product, and all of a sudden the mathematics is way easier than it was before. Especially if you are dealing in 3 dimensions. So we've got, I'm going to just write my vector V out as a column vector 3, 2, 1, and my vector W out as a column vector 4, -1, and 2. I hope you can see the dot product, the crashing into each other a little bit easier there. So what we are having with the vector V, you imagine a vector starting at the origin and going to the point 3, 2, 1 somewhere in 3 dimensions. And then you have another vector W starting at the origin and going to the point 4, -1, 2. It's hard to visualize. Can you imagine I have a hologram here and can see those vectors? And then if I took this hologram thing and turned it so that it was perfectly flat, you would see, oh, there's an angle between those two vectors. Right? That angle would stay the same no matter how much I rotated that box. Or the cube. Holographic cube, I have it right in front of me. It's not showing up on the video, of course, but you just have to imagine that if you're watching somewhere. Okay? And to attempt to figure out that angle using your trigonometry and your math that you have up till now would be very difficult. Because the angle between them in 3 dimensions, eventually you could turn it flat and put it on a piece of paper and try to solve it in 2 dimensions. But that whole process of thinking of it in 3 dimensions, how would you change the mathematics so it was back in 2 dimensions, and then once you have that, you could use your cosine law to find that angle. Whew. But with vectors, we can find the length of V and the length of W, square root of 14, square root of 21. And then cos of theta is just equal to the dot product over both of those lengths. And you can have your answer in radians or degrees. It's just 45.6 degrees. Now we're not going to take the time to prove that formula, but that might be something you want to look up online. Like, how is it that the dot product has that formula for cos? And how is it related to the cosine law? Because once we have this, that's super easy. if we had lots of time, sometimes I have a vivid imagination. I think, what would it be like if whenever you wanted to do something, but in real life you don't have time to do it, you could just pause real life. And then it'd be like, you can do whatever kind of mathematical, like, it'd be awesome for studying for tests, right? Oh, I'm running out of time. Just hit pause. And now I can study and take my time as long as I want to study for this. 1 minute before the test, and then push unpause. And then, right? So if I had this ability, then I would actually, before I showed you the dot product, give you this question in 3 dimensions and say you have as long as it takes to figure this out. You will not age during this time. You don't get hungry. You don't get thirsty. You don't have to go to the washroom. All those common excuses you try to do to get out of work will not work at all. How long would that take us to figure out? 2 years. That's the longest math class of my life. Because my teacher paused time. So now we have 2 vectors in 3 dimensions. And we want them to be perpendicular. So again, one vector is 2m, m, and 8. And the other vector is 1 and 3m and negative k. And we need those to be orthogonal. So, if 2 vectors are orthogonal or perpendicular, their dot product is going to equal 0. So I do the dot product. I get that equation. I set it equal to 0. It's a quadratic. So we either have to factor or use the quadratic formula. It factors. I think that's coming from another class.
Is the negative just a -1?
Yes, thank you. Thank you. That's so easy to make that mistake. All those letters, and if they're bolded like they are in the notes, it's hard to see which ones are vectors and which ones are. Because the I, the J, and the K are just the unit vectors. So given the vector u, and I changed it to a column vector there, 4, -3, give a vector that's parallel. For parallel, I would not use the dot product. All you have to do is multiply it by some number in front, any number you want, and you would get something parallel. Technically, is a vector parallel to itself? Yes. So technically, if you just rewrote the same thing down, it would still be parallel. So I chose 3. I multiplied it by 3. Any scalar product, any number in front, would make it parallel. To make something not parallel is super easy. You can probably guess any 2 numbers and you will be right. But you should double check it because someone's going to be a bad guesser and guess two numbers and not be right. You can have fun. You can do the scalar product and make math mistakes, and you will get the right answer. Because if you multiply by 3 and make mistakes on both of them, and multiply the first one, get it right, but the second one you get it wrong, it will not be parallel. Most likely. But I would have to double check it with my math just to make sure. But when they ask for orthogonal, now you have two different ways you could do it. You could do the dot product and say I need something to be 0. That would probably be more helpful with 3-dimensional. If you could go back to grade 10 math and say, what do we know about slopes of perpendicular lines? The slopes are negative reciprocals. So if we have this slope is negative 3/4, our slope has to be 4/3. And if our slope is 4/3, then that would be flip the vector and make it a different sign. But I'll show you with the dot product. So we started with 4 and -3. We're going to do dot product with two things, and we need it to equal 0.
So is that your little game here?
Yes. I can. Took them longer to find out you were.
I'll put the slope on this right, so.
Okay. If you wanted to, you could pick, I could pick any number to go here. 7, that's not a very nice number. 700 would also not be very nice to use. Okay. I will tell you that my life will be easier if I pick a multiple of 3, but let's say I randomly picked 9. 4 times 9 is 36. I need -3 times something to also be a 36, but negative. This would have to be 12. And that is another right answer because the dot product would be 0. If I pick 7, I could still figure it out, but it'll be a fraction and not very nice, but still right. So you could use the dot product for this. Choose any number for the 9. Do the mathematics to figure out what the other number would have to be so that your dot product is 0. And it would also be orthogonal. All right, I want you to try example 6 on your own. All right, let's see how you did. If they are parallel, then the slopes have to be the same. So x/2 and -3/1 have to be the same. Or you could think of these as column vectors. We have 2x and we have 1 and -3. And you can make them equal to each other and put a k in front of one side. I think I would put the k there. What does k have to be to make them equal? A 2. Pretty obvious from the top part that k would have to be 2. And then something, can I put this in the wrong way? Oh yeah, then 2 times -3, then x would have to be -6. Pretty obvious from that as well. So 2 different ways of doing that one. If they're perpendicular, the dot product, so again, we have 2 and x dot product with 1 and -3 becomes 2 minus 3x, that has to equal 0. So then x would have to be 2/3. Or purple line here separates two different methods. You could use the slope method. The slope method of the first one is x over 2. The slope of the second one is -3 over 1. We make it the negative reciprocal 1/3 and solve. I like the dot product here. And you'll find you'll like the dot product even better once you get to 3 dimensions. Because how do you write slope in 3 dimensions? You have like rise over run over up and down. Depth. Rise over runner over depth. There you go. I like that. Have a fraction and fraction and fraction. Oh yeah, these vectors are written a little bit weird. We have a 3t plus 1 in front of the eye, another t plus 3 in front of the eye on the other one. They are perpendicular. I want you to try this one on your own. All right, if you are done, you can check to see how you did. The dot product would have to equal 0. Set it up, you get a quadratic, and you have to solve.